It's a pleasure to welcome Ada Siffert of University of Münster, speaking on construction of R-harmonic submanifolds.
Okay, thank you very much for the introduction and for the invitation, of course. Everything I say today is joint work with Jose Balado, a PhD student of mine. So as you said already, I will talk about the construction of R-harmonic submanifolds in cohomogeneity 1 manifolds. So the ambient space will always be a cohomogeneity 1 manifold. And my talk is divided into two parts. In the first part, I will introduce the necessary background, and in the second part, I will state the main results and discuss them. So let me start with the introduction. Throughout the talk, Mg and Nh will be closed Riemannian manifolds. And phi will always be a smooth map with domain M and target N. Such a map is called harmonic if and only if it's a critical point the energy functional E phi, which is defined this way. And harmonic maps are a classical research area in differential geometry, which received a significant boost in the 1960s by work of Eels and Sampson. And being a critical point of this energy functional is equivalent to the vanishing of the so-called tension field, where this tau here denotes the tension field, and the tension field is defined to be the trace of the second fundamental form. And examples of harmonic maps are, for example, harmonic functions. And if phi happens to be an isometric immersion, then phi is harmonic if and only if the image phi m is a minimal submanifold of the manifold N. So this is well known. And one generalization of harmonic maps are so-called biharmonic maps. And they are defined to be critical points of the so-called bi-energy functional. And one can do a straightforward calculation, determining what this means, and then you will get that this is equivalent to the vanishing of the bitension field, where this bitension field is given as follows. Tau 2 of phi is defined minus the Laplacian, the rough Laplacian of the tension field of phi plus the trace of the curvature tensor of the target manifold, where the first entry is the tension field, and these are d phi. Okay, so this is all well known, and in local coordinates, this equation here constitutes a fourth order elliptic system of PDEs, and this here is a second order elliptic system of PDEs. So, and it is obvious that a harmonic map is biharmonic. Therefore, in the following, we will always be interested in proper biharmonic maps, meaning we are only interested in non-harmonic biharmonic maps. So let me just proper biharmonic map means non-harmonic biharmonic map, and I will probably not always say proper in the following, but I'm always talking about proper biharmonic maps. Yeah, the other ones are not of interest to us. Furthermore, I need another notion. So M is called biharmonic submanifold of N if and only if phi is biharmonic isometric immersion. And biharmonic is another word for two harmonic. So in the title, I said R harmonic submanifolds. So for the specific case of R being two, one also says instead of two harmonic, one also says biharmonic submanifold of N. And of course, the research on biharmonic submanifolds is quite an important area nowadays in differential geometry. For example, names which should be mentioned are Cesar Unichuk, Stefano Montaldo, and Cadeo and Balmu, and Simona Nista, who have worked recently on this research in this research area. And one thing what holds true in general is that the existence of such proper biharmonic maps seems to depend heavily on the curvature of the target manifold. That what can, for example, be seen in the study of the heat flow, which was studied by Lam. And another instance of this general heuristics is the so-called Shen conjecture, which states that every biharmonic submanifold in a Euclidean space is minimal. So that's still open in general. And this is another instance. So I will briefly say a few words about R, the case of R being larger than 2. So more generally, one can define higher energy functionals as follows. So higher energy functionals as follows. If R is 2s, 2s, where s is a natural number with s being larger or equal than 1, we define the R energy of phi to be 1/2 integral over m of the Laplacian to the power s minus 1 of tau phi squared times the volume form. And similarly, if R happens to be 2s plus 1, then we define e to s plus 1 of phi to be 1/2 of m sum from j to 1 to n nabla ej of this expression here, where the ei constitute a local orthonormal frame of m. And one can now do a similar calculation as above and determine the corresponding tension fields. So I don't want to do this here. I show you the expressions. So I copied them before the talk. So you see, for example, the expression for the case of R being 2s. So you can calculate them in terms of the tension field, tau, and the Riemann curvature tensor of the target manifold. And similarly, you can do for the case where R is 2s plus 1. So all you should keep in mind is that you can do this calculation. The specific form is not of interest for this talk. So this calculation had been done by Maeta. Okay, now this finishes the introduction on these energy functionals. So I said in the beginning, we are interested in the construction of R harmonic submanifolds and cohomogeneity 1 manifolds. Let's first focus on the case R equals 2 for simplicity for this talk. Yeah, so in the following, we mostly focus on R equals 2. So we want to construct 2 harmonic submanifolds. And as I said before, they are also called biharmonic, and I usually call them biharmonic submanifold. Yeah? And I said also already that this is, we have to, in order to provide such solutions, we have to provide such submanifolds, we have to provide solutions to this system of PDCs, which is a fourth order of semi-linear elliptic PDCs. And providing solutions is, of course, hard in general. And the main strategy, which is used a lot of times in geometry, is to impose symmetry, to reduce this system of fourth order semi-linear elliptic PDEs to a system we can deal with. And let me say what the goal is. The goal is to construct new examples of biharmonic submanifolds of cohomogeneity 1 manifolds, and so construct new examples of biharmonic submanifolds, cohomogeneity 1 manifolds, and to write a unified framework for some of the existing examples. So the most prominent examples, which were found by Young in the 80s, are the sphere of radius 1 over square root of 2 in Sn plus 1. And this is an SON plus 1 invariant immersion. And then, of course, the generalized Clifford tori, so tors, sorry, SK 1 over square root of 2 cross Sn minus k 1 over square root of 2 in Sn plus 1. So, and as said, this can be found in work of Jiang. And there are many more examples. Yeah, I just want to mention the 2 because they fit very well later in this in this framework, and I will mention them again. So I have to introduce a bit of notation for cohomogeneity 1 manifolds. I know that we have seen this a few weeks ago, and that most of you know, but in order to fix the notation, I will do this again briefly. So throughout, Mg is a compact connected Riemannian manifold. G, capital G, is a compact Lie group, which acts on our compact connected Riemannian manifold, and the action is supposed to be isometric, and we also impose that the orbit space is isometric to a closed interval of length capital L. So I denote the length of this by capital L. So this standard example is SON acting on the sphere. Then the quotient map is denoted by pi. So that's the quotient map. The fibers of T, where T is in the open interval 0L, are principal orbits. So in this example here, everything projects to this closed interval, and this is an example for one of these principal orbits. And the fibers over 0 and L are non-principal orbits. In this example here, exactly the north and the south pole of the sphere. Then we also have to fix a normal geodesic. This means geodesic within the manifold which intersects all the orbits perpendicularly. So this is one fixed normal geodesic, and of course, in general, the choice is not unique, but we fix one such that gamma 0 lies in this non-principal orbit, gamma L lies in the other one. And it's also well known that the isotropic groups at gamma T, where T is in the open interval 0L, are constant, and we denote these constant isotropic groups by capital H. Then there's an invariant smooth metric G on the regular part of M, so the union of the principal orbits, such that G is dt squared plus gt for T in this open interval, where this gt constitutes a smooth one-parameter family of metrics on G mod H. Yeah.
Oh, excuse me, Anna, there's a question that
oh, sorry, I didn't see it.
Asking, is the action free?
Do I need this? Yeah, I think we yeah, I impose this, yeah. For the moment. I haven't thought about this if we really need this, but I think yes. Yeah. Okay. For T in the open interval, we have the orthogonal splitting of the tangent space into the tangent space of the orbit plus well, normal space, and this normal space here, this is spanned by gamma dot t, yeah, so one-dimensional. And I'm almost done. Q denotes a fixed bi-invariant metric on G, and the Lie algebra of this capital G splits into the Lie algebra of the capital H and its orthogonal complement, which we denote by N. And then there is a endomorphism PT from N to N, yeah, endomorphism, yeah. And this is, well, in fact, there's a smooth one parameter family of Q-symmetric at H equivalent automorphisms PT, which are defined by G X star denotes the tension field of X, where X is an element in the Lie algebra of G, and similarly for Y. So this is defined as follows, yeah? And X star P at P is the action field associated to X. So this means that this is this way. Okay, so, and this endomorphism will appear later on when we determine the condition for some hypersurfaces in cohomogeneity 1 manifolds to be biharmonic. And this family PT encodes the matrix GT and contains information about the extrinsic geometry of the principal orbits. For instance, it is possible to express the shape operator of the orbit G dot gamma t in terms of these endomorphisms. Yeah? So ST is the shape operator of the orbit G dot gamma t, and one can show by a straightforward calculation that we can encode this in terms of this PT, and that this formula holds true. Yeah, so this formula already shows that this PT is of importance. So I'm almost done. That's the last thing I want to introduce. In this work, we restrict ourselves to a special class of metrics that will be of particular usefulness. Yeah, we suppose that N, this orthogonal complement of H in G, splits as N1 plus 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 NL. So this is a decomposition into mutually orthogonal H at H invariant subspaces, and then consider the metric along gamma t, and we will impose that this is of the form of this form, E from 1 to L, where these Fi are some positive functions satisfying appropriate smoothness conditions as t converges to 0 and t converges to L. I don't want to go into details here. That can, for example, be found in the work of Wolfgang Ziller. And of course, Q is a bi-invariant metric on G as above. And this resulting bi-invariant metric G, so then G is called diagonal homogeneity 1 metric. And in this work, we are interested in diagonal homogeneity 1 metrics only. So this finishes the setup part. And now, with the help of this setup and this notion I introduced, I'm able to state the main results. And as I said, this endomorphism PT will come in again. So let me state the first main result, that's theorem A. Throughout, MG will always be a cohomogeneity 1 manifold. The orbit space is isometric to a closed interval 0L, and we will impose a diagonal cohomogeneity 1 metric. Yeah, so I don't write this again. We consider the isometric immersion iota of the principal orbit into M. And we want to examine this one for biharmonicity. And then the tension field, that's a tau, of this isometric immersion is -1/2 of the trace of PT inverse PT dot times T. So this T is the unit normal field to the principal orbit. So that's the unit normal field to principal orbits given by T at gamma, at G dot gamma T is G dot gamma dot T. Yeah. And more important for us, the bitension field of iota is given as -1/2 as of trace the inverse, the second derivative of PT times the tension field of iota. Sorry, iota, not tau. Yeah? So these are the formulas we get. How do we do this? Yeah, okay, we simply use these formulas here and use this geometric setup I just introduced and do the calculation for the tension field and the bitension field. So I don't want to go into details here because it's just plugging in, doing some calculations, and then rearranging, and then finally getting these formulas. So the difficulty is just in finding the right setup. Yeah, doing this calculation is not very hard. Yeah, one can now, with this theorem, recover some of the known examples, namely the examples I mentioned above, the these two. Yeah, one can recover these examples. They exactly fit into this setting, and one can construct new examples. And I want to I just want to provide one of the old ones and one of the new ones. So the old one I do is the sphere of radius 1 over square root of 2 in Sn plus 1. So we take the round sphere, endowed with the natural SON plus 1 action, and the orbit space, the orbit space then isometric to the closed interval of length pi, and the normal geodesic we fix is cosine t psi1 plus sine t psi2, where these psi I runs from 1 to n plus 2, constitute the standard basis of the Euclidean space Rn plus 2. And we take the bi-invariant metric trace of x transpose times y, where x and y are in this orthogonal complement of of h in G, so in N, yeah. And in this case, we can write the metric as d squared plus sine squared t times q restricted to n, and thus the endomorphism pt is given as sine squared t times the identity, times the identity. Consequently, the equation here, trace pt inverse, which is the condition for the hypersurface to be biharmonic, is equivalent, just plugging in, to cotangent square being 1. And this is the orbit SO n plus 1 times gamma pi over 4 is proper biharmonic. And this recovers exactly the already known example I mentioned above. So this recovers this example in this setting. A new example I want to mention is the following. So it's well known that the complex quadric, so that's the thing I want to study, the complex quadric, which can be considered to be the quotient of SO n plus 2 divided by SO2 cross SOn, admits a cohomogeneity 1 action. By SO n plus 1. Then one can take representing geodesic, which is also well known, which can, for example, be found in work by Urakawa, and take an inner product as follows. Then one does a straightforward calculation as above, finds that PT is given like this. And then the equation here, which we want to study, is equivalent to this equation here. And now one can easily solve this equation. For example, one can substitute x equals cosine t squared, yeah? And then one can see that SO n plus 1 times gamma pi over 4 is a proper biharmonic hypersurface in Qn, in the complex quadric Qn. And this hasn't been known before, to the best of our knowledge. Okay, and then one can do other examples. I don't want to do this. Instead of this, I want to state the second main result. And again, as before, Mg is a cohomogeneity 1 manifold. The orbit space is supposed to be isometric to a closed interval. The metric is supposed to be a diagonal cohomogeneity 1 metric. Then we consider the isometric immersion iota again. So the principal orbit is immersed in M. We denote by alpha minus 1/2 of trace PT inverse PT dot, and beta 1/4 of this trace here. Then under this, with this shorthand notation, one can now calculate the R tension field. Remember that this was this awful expression I showed you in the beginning. One can now show that this R tension field vanishes if and only if beta times trace of PT inverse times PT second derivative of PT equals 2 minus R divided by 4 times alpha times trace times this expression here. And of course, yeah, this is a rather simple equation, and we only get this kind of simple equations due to the fact that we impose a lot of symmetry. Yeah, so we imposing that the ambient space is a cohomogeneity 1 manifold, and we are considering this immersion. Yeah, we just consider the immersion of the principal orbit into this cohomogeneity 1 manifold. Let me do one example. And this is also new. Let me consider again the complex quadric, which I just discussed. We have seen that PT is given like this. And now one can just plug into the equation and see that one has to solve the following equation. So one sees that an orbit is proper aharmonic if and only if x is a root of the polynomial px, which is given as r times n x to the power 3 plus n minus 2 minus r from where we obtain R harmonic orbits for every R. Yeah? So this is a rather simple task. Yeah, and as I said, this is new. Okay, so in the last 5 minutes, I thought I would have more time, but in the last 5 minutes, let me just explain briefly what we also did. So it is well known, it has been shown by Montaldo and Onichuk that the sphere S7 doesn't admit a compact proper biharmonic hypersurface with constant mean curvature and 3 distant principal curvatures. So this has been known, and a question we addressed is the following. To what extent is this property characteristic of the round metric? Yeah? So they studied the round metric, and we wanted to study whether all metrics satisfy this property. We used, to answer these questions, we used the techniques I just presented in the previous sections. And the strategy consisted of starting with an isoparametric foliation of S7 with 3 different principal curvatures, and deform the metric while we keep the homogeneity of the hypersurfaces. And we made use of the so-called Shiga deformations to do this. And this is a deformation of metrics which was used by Shiga to study manifolds admitting metrics of non-negative sectional curvature. And we did so, yeah, so I don't have time to go into details here, but we showed that we can find a deformation of the metric such that in the end we get a proper biharmonic hypersurface with 3 different principal curvatures in S7. Yeah, so that's what we showed. So I will stop here, and thank you very much for your attention.
You certainly have more time if you wanted to say more.
I thought I had 50 minutes, and the problem
it's been less than 45.
Okay, so my watch tells me it's 45. Okay, so
and if you 50, we say
I think I would need 20 minutes to explain this in detail.
Oh, I see.
But I can
if you want to take
I can just say
15 minutes,
what I just said. Yeah, so S7, yeah. So we can, what I can explain briefly is, so we again consider a diagonal cohomogeneity 1 matrix. We can perform a Shiga deformation on the homogeneous part. So, and let me ST, yeah, just. And the metrics GS are also diagonal cohomogeneity 1 for every positive parameter S, yeah, and the endomorphisms PST, which I'm interested in, are given by PST PT times. So that's a straightforward calculation we did, yeah, and of course PT equals P0T, yeah. So we performed this Shiga deformation and did a straightforward calculation to get this formula here. Now, with this formula, we studied the case I just mentioned. Yeah? So we studied isoperimetric hypersurfaces with G equals 3. In the case of 3 different principal curvatures with multiplicity all 2, the isoperimetric hypersurfaces in S7 are tubes of constant radius of standard Veronese embedding of CP2. This is, of course, well known. And then for this setting, PT is given for this cohomogeneity 1 setting. For the for the isoperimetric hypersurfaces. Yeah. So the PT 2P3 is given this way. Yeah. Now plugging in this formula star, so meaning performing a Shiga deformation, we obtain that PST is given and similarly for the other entries, yeah, 1, 2 divided by 1 plus S sine squared sine, and the third one completely analogous, yeah. And then remember that the biharmonic equation reads PST inverse PST 2 equals 0, yeah. Where the derivative is taken with respect to t, of course. And now if S happens to be 0, so S equals 0, then 2 true star is equivalent to 2 for x minus 3 squared x equals minus 1, where x is cosine squared t. So there are consequently no proper biharmonic orbits in G0. Yeah. So, and by continuity for small values of S, the identity here, 2 star, admits no solutions. However, if we deform the metric enough, new solutions appear. For instance, if we take S equals 1, then in this case, one can see that 2 star sorry, there's a 1. Evaluated at t equals pi over 6 is less than 0, is less than this evaluated at t equals pi over 4, sorry. Hence there exists some value between pi over 6 and pi over 4 such that this expression 2 star vanishes. Yeah? And that's how we constructed a metric such that a biharmonic hypersurface exists. Yeah? And the only thing which remains to be checked is that this is not minimal. And we did this by a straightforward calculation, proving that this biharmonic orbit we constructed is not minimal. So that's how we used Shiga deformations to construct biharmonic hypersurfaces with 3 distant principal curvatures, but not with the round metric, of course. Okay, so then I will stop here.
Thank you.